Okay, you guys see, hope the font you can see. These are some of the stop words the model or the framework believes it's not going to help. And you can eliminate these stop words in one single stroke. And if you feel some of the words are useful, you can keep them, but you need to just go back to modify the dictionary of the stop words. Okay, let's get to you might have heard of something called sentiment analysis. Every company does sentiment analysis. Yeah? Yes? No? You know, when I first started teaching as a hobby long time ago, when I was still young, I wanted to ask a professor, how do I know that the audience are still engaged since they are listening to me? Oh, he says a simple thing. Just ask a couple of silly questions. Are you there? Are you listening to me? And if you feel an emphatic yes, then they're still engaged. If there is whatever and there's no response, maybe it's time for you to take a break. So let me ask the question again. Have you heard of sentiment analysis? Yes. Okay, fantastic. Okay. Which only means that we're going to take a break a little later, not now immediately. Sentiment analysis using text is a solved problem almost 2-3 years ago. If you are, let's say, a new car company or a product company like a phone company, and if you want to find out how the audience are feeling, you can get a product level feedback immediately, and that problem has been solved 2-3 years ago using NLP. But off late, I think it's more of the feature level feedback. Yes, I like the phone, but the screen is really bad, the resolution is fine, cameras really suck. If that's the feedback you're getting, you want to know immediately. But I'm going to show a product level feedback, and I want to show how simple, extremely simple, is to figure out sentiment. So I have a data set. So if you have downloaded my entire set of files I've given in GitHub, there is a .csv file called tweets. If you want to open it, you can open it and see. There are around 9,000 tweets in it. So I'm actually going to develop a model right in front of you. Actually, I've already written, I just need to run it. And it processes and identifies the sentiment of 3 sentences I've put in the file. I want you to see how simple it is to develop a sentiment analysis model. I want you to appreciate that the corpus, the data set, is such a small data set. It's 9,000 tweets. Half of them are positive tweets and half of them are negative tweets, so that the model can understand what's positive, what's negative, or no feedback. That is neutral. So 1/3, 1/3, 1/3. And also I want to see how sometimes model is intelligent or not intelligent. Okay? So I'm actually going to open Python, and I'm actually using an older version of PyCharm. So what it does is it actually closes every time because I don't have a license. I'm actually going to open it again. So classifier.py, if you want to open it. And the interpreter I'm going to use is 3.6. And you can do anything else, but I think it works. It's 3, but not 2. Python 2, it may not work. So here is the 2 data points I want you to take away. Look at the number of lines of code. 24, including blanks and including my inference statements. This model is going to do a sentiment analysis of 9,000 tweets in a split second. And it will also identify what the sentiment is for this sentence. This is fantastic. iPhone not bad. iPhone cost too much. Okay? So let's see. Hopefully it runs without any complaints. There you go. The first one, it says positive emotion. Second, okay, let me push this up. I don't know whether I can increase the font size. Hopefully you guys can see the font at the bottom. iPhone not bad. no emotion toward brand or product, and number 3, iPhone costs too much, negative emotion. If you guys can, if you're able to run it on your laptop, change that text randomly whatever you want, a negative sounding, positive sounding, and see if it's smart enough to figure out. Oh, this is so fantastic if I had $1 million, because you're putting a sarcasm in it. Yeah? Sometimes people put a sarcasm, but they're using positive words. Oh my God, this is such a fantastic phone, only if I had $1 million, which means it's really a bad phone for the money they're charging. And put that sentence and see if it figures out or not. But remember, this indeed make mistakes too. The accuracy is not 100%. It does make mistake. And one of the primary reasons for that is the data set is very, very small, number 1. It's only 9,000 data set. But there's another interesting aspect for why this is not very accurate, and I want people to take a guess. If you can or cannot, then I'll tell you the right answer. There's one more data point why I think it's not as accurate as you can think. Let's say if you have 4 other sentences, 5 other sentences, I think sometimes it may not figure out. Yes, sir.
Yeah, okay. So I have tried to solve this problem. One, I found out you can either give them a hot list of positive words and negative words that comes from professors that covered in Chicago. And another is that Python, they have a package recently became popular because they run actual survey and they made a tool which actually asks people and from that they figure out. And I think this must be doing statistically.
No, this is actually running an NLP model. The statistical models which were done a few years ago, those are not scalable anymore. So that's why I think the whole machine learning and AI, deep learning is getting really popular, because you don't have to use any of those non-scalable models anymore. This can scale fantastically. And so, but I'm only showing here just for 9,000 tweets as a classroom assignment. Anyway, going back to my second question on why the accuracy is low, can you guys predict anything? Yeah. I am not sure whether the sequence of the words it's actually figuring out. What it's figuring out is it's actually getting the overall sentiment of a sentence. Let's say if you say, this is a bad phone and this is a good phone. This is not bad phone and this is a bad phone. It will figure out not bad, negative, double negative is actually a positive. It will figure out, because if you have given enough data. It's not doing a pattern matching. It's not looking for a specific word. It's not statistical anymore. So I'm not sure if I understood your comment correctly. I don't think that's the answer. But
yeah, one more way you can do it, you can count each word.
No counting. There's no counting. This is not statistical anymore. This is deep learning, NLP. Any other comments why the data data is wrong? Open the Excel sheet. Sorry? Oh, okay. Well, sure. There are different models, especially 2-class classifiers. There are so many models available. Individual models sometimes may work. Some individual models may work well in some cases, and some other cases it may not. And people use an ensemble where they collect multiple models. Yes, sure. That's a possibility. Sorry, yeah, I didn't think about that. But there's another one which the answer which I'm looking for is not that. You had a comment, sir? No, that's what I said. If you use another model, let's say XGBoost or decision trees or whatever, you may have similar inaccuracies, but the inaccuracy could be somewhere else. It may not be 100% accurate. Where? Yes, that's it. Whenever you do a machine learning solution, the effort you spend in developing a solution should be only 20% of the effort. 80% of the effort, you got to understand the data. You got to go check the data. It's like you fall in love with the data. You got to keep looking at the data. Especially if you don't feel like sleeping in the night, you should keep looking at the data. In this case, if you open it and do a little bit of a permutation combination, you can do a little bit of ordering, you'll find, I don't know whether it's the negative sentiment or the positive sentiment, the number of tweets available for a negative sentiment or a positive sentiment, I think they're not enough. So the model is not becoming intelligent enough to figure out the negative sentiment. It may be intelligent enough to figure out the positive sentiment, because out of the 9,000 data set, even if you look at the percentage distribution of the data for each class, in this case the class being positive, negative, and neutral are the 3 different answers or 3 different classes. You should have enough amount of data, number one. You should have balanced amount of data too, for the model to become intelligent. And hence, if you are really interested in ML, I'll give you a problem statement. Maybe you guys should go back and think about this. Let's say you're a bank and you're trying to do a fraud detection, credit card transaction frauds, okay? Typically a bank, let's say you're a Citibank or a Wells Fargo, whatever, and if you have you may have almost, let's say, 1 billion transactions per month maybe, and the number of fraud transactions will be, let's say, maybe 100 or 1,000, let's say 10,000. But what's the proportion of this 10,000 in 1 billion? So 999,000,000, whatever, are all positive transactions, and you have a few negative transactions. And if you give all this 1 billion transaction information to the model becomes extremely intelligent to figure out what's a positive transaction and does not have enough information about a negative transaction. But here is a kicker. If you have such a unbalanced data set, you don't need a model. You just say, okay, I'm going to be the model. Every transaction is a fair transaction, because you'll be still 99.999% accurate, because 99.999 times the data is right. There's not a fraud transaction. How would you define a model in such a context? Think about that. That's not NLP, but just for the heck of it, I mentioned that. Yes? To go where? To go where? Mm-hmm. Yeah, I don't know the answer. Good question. It's counting the sentences which are positive and negative. I think I was answering about the count there was, I think it's not counting the words. Which, okay. Yeah. You may be right. You may be right. I'm wrong on this, but this may be a wrong example then. I'll take that back. Yeah, sorry for that. Okay, let's get back to okay. I'm going to start the real NLP deep learning models now. The fundamental building block of NLP is recurrent neural network, RNNs. RNN is a type of neural network which actually takes word one by one, processes it, updates something called a hidden vector, and the hidden vector actually is capturing the essence of the input so far. If you say, Sally went to the kitchen, John went there too, and after these 10, 15 words, you input into RNN, and if you look into the hidden state, it's of course a bunch of numbers, you can't actually make sense out of it, but this bunch of numbers, which is called hidden vector, capture the essence of the feed you have given till now. That is the most fundamental building block in deep networks in NLP, because you have a series of text coming in, unlike in statistical machine learning or in image processing, where you have one image that comes in which may not have a correlation to the next image coming in. Similarly, for statistical analysis, if you're doing an email campaign response, which I mentioned to you earlier, each user, each customer who responds to email campaign is so different from the other person. So you actually can imagine every customer is a random customer. But in this case, you have the first word, the second word, third word, many times. The previous word was dependent on the current word, and sometimes the future word may be dependent on the current word. So there is a lot of dependencies, and there's all temporal aspect. One comes the word after. So it actually starts from the left to right. The model starts looking at word number 1, word number 2, word number 3, word number 4. It starts assimilating and synthesizing and keeping the information internally. What is the meaning of synthesizing? How does it synthesize? What information it keeps? How much of information it keeps? All of those questions we'll answer. And this is, RNN was invented, I think, some few decades ago, but I think the application of RNNs are happening more prevalent in the recent past, last 4 or 5 years. But in NLP, the using RNNs to process it, and it started around 3-4 years ago, maybe 5 years ago, more of 3-4 years ago. And in the last 1 or 2 years, there are other variations of RNNs that have come, which we'll talk about. But at this point of time, I want you to take the message. So you have X is an input, which is actually a word. Y, U, V, W are matrices, which actually are processing information. But I'll talk about those details later because they're going to get changed later on. T, T minus 1, T plus 1, these are all time steps. That is, at every word when you input to the model, it actually, it's a time step. So you actually move from one time step to the other time step. And every time step, the RNN is updating its hidden state. Whenever you understand RNN, the most important factor I want you to take away is the hidden state. That is the most essential component of RNN, and we'll talk about that. And we'll talk about other variations of it. But RNN, that's what an RNN is. I remember I talked about Shakespeare's a novel. There's a gentleman by name Andre Karpati. He's an extremely smart guy, PhD from Stanford, and he's taught there. Right now, he's the head of ML in Tesla. There are 2 people I admire the most. A lot of other people too, but in terms of ML, machine learning, there are 2 people. In NLP, there's a gentleman by name Richard Saucher. When you hear him or see him or meet him next time, tell him I said this, that he's like God in NLP. The amount of contributions he has done for NLP is just mind-boggling. And he right now works for Salesforce. Yeah, that's one gentleman in NLP. Similarly, in image processing, there was another guy, another god called Andre Karpati, and that's the guy I just now mentioned about. He's developed a model here where he trained a RNN, not RNN but Lsdm, but I'll talk about that later. But let's say he trained an RNN with all the novels of Shakespeare. This is Shakespeare, right? In this case, yeah, Shakespeare. And after multiple amounts of training, and when he asked the model to start writing a new story, it actually started writing a story that sounds and looks similar to Shakespeare's stories. Of course, there's no plot in it. Maybe the intricate plots are missing, and sometimes it does give out some gibberish. But if you look into the commas, the periods, the length of a word, and length of a sentence, how many words you can have. Look at even words like alas, which seems to be like a Shakespearean language. And also, it identifies the names of the roles, and the names of the roles are in caps, whereas the sentences or the dialogues the roles are mentioning is not in caps. It is amazing in terms of how accurate the model figured out how Shakespeare writes and starts writing it. Of course, the sentences may not make real sense, but this is a training he has done using RNNs, actually a variation of RNNs.
Yeah, I just wanted to share a real-world application of this. Harry Potter writer, she wrote a non-Harry Potter novel without using her full name. And she never let anyone know that she wrote it. Some people, some journalists, by running this kind of model, they could figure out she's the one who wrote it.
Oh, okay.
After they're doing it, then they
Yeah. Today, sorry.
It could prove that it is her writing.
Sure, yeah. You can train a model to figure out who the author is. Yeah, absolutely. Today we'll be doing one exercise. It's called Generative Model, which actually generates text. I have a smaller model and a bigger model. I have trained both the models. The training of the model for the smaller one took almost 35-40 hours. on my regular iMac, not GPU. The bigger model, it took almost 66 hours, I think, on my iMac again. Because the model is already trained, you don't have to train it anymore. I have given the weight, so I've given the model to you. You can run the file, it run the model, and it actually starts generating a text. In the small model, it generates just a sentence. You can see it comes, well, it's gibberish, but it actually comes closer to what a human being would be writing. And if for a bigger model, it actually generates 100 to 150 words a paragraph, and it sounds more like a human being's language. Of course, it still outputs some gibberish, and sometimes it repeats the words and stuff. Some of the problems, what you normally find in generative models, what you will find hands-on. But that's more of a 1.5 to 2 years ago research, but you'll actually be able to do that development yourself. It's 9:47. Too early? Not to leave for the day. I'm just taking a break. Okay, wait, maybe another 10 minutes? Yeah? 10 minutes, okay. I appreciate the assertiveness in that. 10, that's it, okay. RNNs have a problem. If you feed word by word in a series, after some time, RNN starts forgetting slowly what was the first word, what was the second word, what was the third word. It starts forgetting. In other words, what's the capacity of RNN? Experts say somewhere between 8 to 10 words. After 8 to 10 words, it starts forgetting the first word slowly. The moment you put the 11th word, it would not remember what the first word was. So if you're using that model to, let's say, oh, let's do a language translation. I give you a sentence in English, and then I want you to do a French translation. And if you have a 15-word sentence, it'll forget what the first few words were. And if those were influencing the words that came after, the entire translation will go for a toss. So that's called vanishing gradients or exploding gradients. That's the two different problems for RNNs. We won't talk about what the exploding and vanishing gradients are, but a new model that came out called Lsdm, long short-term memory. This is a variation of RNN. It also takes inputs one after the other in the same sequence. It also has hidden state. It also has something called cell state, but you compute the hidden state using the cell state. So practically, you can ignore what cell state is. And in other words, to summarize, an Lsdm, the most important output of an Lsdm is the hidden state, like RNN2. But because of the upgrades this RNN went through, it can store information about more number of tokens, more number of words. And according to Chris Manning, the professor in Stanford, he says you should take a number 100. If the input is longer than 100, then Lsdm also starts forgetting. But that's 10 times better than RNN. So Lsdms are a variation of RNN, which take inputs in a sequence, does lots of processing. There's a lot of mathematics right there. And if you want, I can explain that too. The way it does it, it identifies what information to store, identify how much information to store, and what information to forget or ignore. And hence, it keeps a part of the memory open so that it can take at least information worth 100 words. That's the logic. And I can explain the various gates. You have the input gate, forget gate, output gate. But for today's discussion on the brevity, I would say Lsdm is a variation of RNN, which actually takes lots of words as an input in a series and updates its hidden state, and the hidden state captures the essence of the input till now. If you're using Lsdm to do a language translation or a summarization or question answering, you can use the hidden state to ask questions or to summarize or do a language translation, because it captures at least 100 words worth of information. You had a question, sir? Yeah.
I was just curious about this 100 words. So I've checked Google, the latest translate, and it does it. It basically can't do gender understanding. Languages that have gender, even if it's clear from the sentence before. So I just kind of wonder where that number came from, because that doesn't seem correct.
There is a video of Chris Manning teaching the NLP course in Stanford, online YouTube video, and there's exactly this question asked to him, on how many words Lsdm will. He said, for your mathematical and practical applications, take the word 100, but if, let's say, if the language is full of domain-specific words, and if it's too much of specific and loaded words, it may forget information faster. But he says take a number 100. And that's what I'm saying. If you, let's say if you're working for a healthcare or any other startup trying to develop a solution to do a language translation, anything longer than 100, you are sure the inaccuracies will go up. That is, the model will start giving wrong answers. So if you stick to, let's say, 50, the probability of the accuracy being higher just because it remembers is higher. So it remembers all the words, and hence, if you have any inaccuracies in the model, that's not because of the length of the input, it may be some other reason. Yeah, the sliding window, it's only when you're doing the input for training purposes. But if you have, let's say, a training window of, let's say, 5 words, and if you actually do lots of 5-word combinations, that's fine. It takes 20 such iterations and still remembers all the information. After that, it starts forgetting, so you need to actually do something about that to see how to keep that information loaded somewhere. So you actually can do updates of your weights and store some other way of doing it. But that's no. Window size cannot be more than 100 though, by the way. Okay, I'll stop here. That's Lsdm. If you have any quick questions, I'll take the questions, and then otherwise we'll break. I don't know, Janling, what's the duration of the break? It'll come back in 10 minutes? Yeah, I think there's coffee and restroom break if you have any questions. And then we'll start with a yoga exercise. Okay, thank you guys. You cannot do without an LTK. But remember, I just downloaded it in front of you on my computer. It just took 2 seconds. NLTK, everything. I just downloaded everything. So I don't know how fast, but I am using the same Wi-Fi too. Is it? But mine too, I was just doing right in front of you.
Yeah, but all the students are hitting the same file at the same time. There are, what, 500 students?
Yeah, but I'm also like a student trying to download, so I don't know why it took so long time. I took only 2 seconds actually.
But I wonder if there's some buffer that you're... So it picks up characters
words are four character, 5 character long. Sometimes after a last comma comes, a period comes, the caps come sometimes, lowercase, uppercase. It knows automatically. Okay, can we start? NLP is trying to solve so many problems which were thought to be almost impossible. Sometimes you just could not imagine that you can solve this problem too. Even though you had so much of data, there was not enough models available, computing power available, but nowadays you can solve a lot. But talking about impossibility, I want to talk about what's impossible, okay? I'm sure you've heard of something called yoga? Yes? Okay. After the break, at least, you should be able to say yes a little more loudly. So one of the best things, there's so many exercises in yoga people do which actually keeps you really fit. I personally believe of all the yoga exercises, breathing exercises are a lot more important. But I'm sure some people may disagree. But let's talk about breathing exercises, okay? Indulge me. I want you to take a deep breath and do exhalation. You can close your eyes if you want to, or you can keep your eyes open. Normally, people close their eyes, but remember, the exhalation has to be longer than inhalation. Okay? Let's do it. Take care. Okay, you guys are done? Now tell me how long it took for you to breathe in and how long it took for you to breathe out. How many seconds? Few seconds, like 5 seconds, 10 seconds maybe in, and another 5, 10 seconds, or 20, maybe 15 seconds out. Now my question number 1, can you breathe in and breathe out simultaneously? Sorry? Oh, okay, yeah, okay. You know, there is a fantastic English word called stealing my thunder. That's, that's exactly what but anyway, I will still get the message through a different way. I have a different story for that. If you have to play a musical instrument, almost the same thing but slightly, especially a flute or a saxophone, and if you want to hold a note, yeah, you blow it and continuously blow and hold a note. How long can you hold it? Like, ooh, how long can you actually do that with a wind instrument? 10 seconds, 15 seconds, 20 seconds. If I say someone actually can do for 45 minutes, can you believe that? Yes? Okay, yeah. There's a famous saxophonist called Kenny G who has done it, and also Australian Aborigines, actually, they do something called continuous breathing, where you can actually breathe in and breathe out simultaneously, but slightly modified, and hence you can actually play a musical instrument for 45 minutes. Actually, there's a YouTube video. It's not for 45 minutes, it just shows for 4 or 5 minutes, but he could do it for 45 minutes. The only thing is no one is going to watch 45 minutes of the video, so it's 4 or 5 minutes. So you should give a search for Kenny G on YouTube, you'll see that. The point I'm trying to make is the problems that may look impossible, not always are impossible. Some are still impossible, I guess. How to live longer than 100 years, or maybe how not to die could be another problem which I think sounds impossible at this point of time. But there are a lot of problems machine learning is solving, which thought to be, I think, even 2 or 3 years ago, almost impossible, and people are trying to figure out. Before I get back into this, I want to clarify, a couple of people asked me the question about the 100-word limit thing. When you do more than 100 words, you have to let the model to assimilate the information. It does a back propagation and then assimilates information. Now it's ready for another set of inputs. So in other words, while training, it can take millions of words in, but at a gaps of 100 words, and then it assimilates and then goes further. But while inference, let's say if you have a language model or translation model you trained, and you have used a parallel corpora of 1 million sentences in the source language and 1 million sentences in the target language, you train the model on these 1 million sentences, and now you are using it for production purposes. And during production, let's say, for example, you have a Google Translator app on your iPhone maybe, and when you start using it, it waits for you to finish the sentence and then translates. But if you speak for 15 minutes or 1 hour, it's not going to translate the whole 1 hour thing. It only catches for the last 20 seconds, 15 seconds, and then translates it. Okay. Now this is another most fundamental building block. You will see this word sequence to sequence, sec to sec, but sequence to sequence is the model. In NLP for sure, for many, many applications, but you will see this even in some image processing and audio processing too, but beyond the scope of today's presentation. Sequence to sequence model is nothing else but an extremely simple Lsdm or RNN taking a few words in a sequence, and after the input sequence is done, it starts doing an output sequence. So the input is a sequence for the model, and output is a sequence too. Let's take an example. If you're doing a language translation, you give an input sentence in the source language, and the model is supposed to give the output in a target language. So in this case, if A, B, C, and a special token called end of sentence, EOS, is my input, and typically end of statement or a special token for the model is to alert the model that, okay, I've done my job, now do your job, type of alert, and then the model starts outputting. So at time step T1, input is A, and then time step T2 is B, and T3 is C, and at every step, the horizontal arrow you see going from the first box to the second box, that's the hidden state. The hidden state gets updated based on every input and goes to the next step, and the hidden state is transferred to the next step, and based on the new input coming in at that time step, the hidden states get further modified and keeps on going. And after the input C and the hidden state, whatever that comes out, goes to the next box, when the model encounters end of statement, token or any special token, it updates its hidden state. Now it's ready to do its task. And if the model, the training you have done is for translation, it starts outputting W, X, Y, Z, and end of statement, end of sentence token. Now, it keeps on outputting a character by character or word by word, and I'll talk about variations of characters and words in my models. But that's a simple sequence to sequence model. You give an input sequence called A, B, C, end of sentence, and then you get a sequence called X, Y, Z, W, X, Y, Z, end of sentence sequence. That's a sequence to sequence model, and it's the same RNN which actually is taking inputs, and then eventually it does the outputs. That's the essence of a sequence to sequence model, and at a very fundamental level. This was the first model suggested, I think, 2014. Later on, some people said, okay, to improve the learning capability of the model, when it starts outputting W after the first end of sentence, you have the W coming out. Is there a laser pointer I can show, we can use?
I bet there's a cursor on your computer.
I want to actually be facing the people and looking at the people, not into my monitor, that's why. So when you have the first output W, during training, this is the important detail. During training, let's say if W is not the right answer, yeah, its model is learning. If it's not the right answer, you tell the model what the right answer should have been at that stage, but you input the right answer in the next time step. So I can see that side too, but I'm actually seeing this side. The end of sentence outputs, okay, fantastic, thank you, sir. Hope you guys can see it too. I know, I'll try to see it from that side. So you have the end of sentence coming in, and you have the hidden state coming in, and the final hidden state gets, this final hidden state of the input sequence is processed, and because you have an end of sentence token coming in, the model thinks, okay, now it's time for me to give an output. It gives an output W. But what if the output W is not the right answer, or let's say if this is W prime, and if W is the right answer, you give an input, the right answer called W at the next time step. And remember, the horizontal arrow is your hidden state. The hidden state is constantly getting updated, even when it's taking inputs and even when it's giving outputs. So it's constantly updated. And the hidden state at this stage, let me show from this side. The hidden state at this stage the model knows that I have taken the inputs A, B, C and end of state sentence token, and I have also outputted W as my first output. That's what the essence of hidden state at this arrow is. And then when it goes to this arrow, the model knows what my inputs are and what my outputs are till my time. So it actually remembers every time steps what it has done. But going back earlier, as I said, sequence to sequence model, you give a series of inputs and then it does series of outputs. To improve the accuracy of the model, people figured out if you give the correct inputs at every stage, especially during training, the model will know, oh, sorry, I made a mistake, but this is the right answer. Okay, I'll remember that, and keeps on going. And if you repeat this maybe 1,000,000 times, the model knows what the right output should be based on my input during inference. So when you have trained the model, and if it's ready for you for production purposes, and if you're using it, and you give the input and it starts outputting. But the difference between training time versus inference time is, inference time you don't have a right answer. You just don't know what the right answer is. You just have to believe what the model is telling you is the right answer. Because training is done, model is already done. You can do a retraining later on. But so this picturization is during training how a model works, because you are actually getting the right answers. So that was stage 2 or improvement 2. Improvement 3, some people said, you know what? Even during inference, I actually can give inputs, the same outputs as inputs to the model, because the model, even though it has just now outputted W, I'm actually going to give input W as a W in the next stage, because the model can actually better understand what it has done, because it's a little more recent information, even though it's just one time step away. When it does an output W, let's say that is the right answer or the wrong answer. So it has an output. But you know what the right answer is. Loss function. So when you tell what the right answer is, it should have been W prime and not W. So it actually computes a loss function. And because you do a loss computation based on a mini batch, it accumulates all the losses, and when you're done with the mini batch, you go back and update your weights based on the losses. And then now it starts taking the next set of inputs. Yes, yeah, the loss function. So it actually computing the loss function based on the input. So I'll come to the mathematics also, but if you look into fundamentally what you're doing is on a non-mathematical explanation is you have the model outputting some things, and if it's not the right thing, you tell the model what the right thing is, model understands, and then keeps on understanding and improving and start doing it. But in a pure NLP mathematical model is after you give an input, model does some output. If that is a wrong output, you tell the model that's wrong. It does something called a back propagation. It updates its weights to reflect what was its wrong answer and how wrong it was compared to the right answer. It computes the loss. It is a loss function. Every such training model will have loss functions, and we may or may not talk about loss functions. But let's say there is a loss function for this. It understands what was the right answer, what was its wrong answer, computes the difference between the two, and goes back and updates its weights. And it is now a little more intelligent to make a right prediction. And if you repeat this process maybe 1 million times or 2 million times, it actually becomes more and more intelligent and then makes more and more accurate predictions when you start using it for production purposes. So one question in this case is, can we have a 10 million or 20 million if we can have more such data to make it even 100% accurate? May or may not be, I don't know the answer because no one actually found a data set of 10 million, 20 million, maybe a billion numbers. Right now I think people are in NLP areas, you can create data sets for maybe 1 million instances. I've seen some cases, but 200,000, 300,000 data sets, it's 200,000, 300,000 data points data set is what people can find, and models are responding accordingly. The more data, yes, you can find. There is a research which also says sometimes more data is not going to help, but there's no controlled study or a conclusive study to prove whether more data is going to be helpful or not. But at this point of time, the common accepted belief in NLP world or ML world is more data is better. You had a question? Yeah, go ahead.
I mean,
okay.
So
the question is, how do you know the right answer? Yeah. So let's say if you're doing a language translation model, when you're training a new model to do a translation from a source language to a target language, you got to have a sentence in source language and a complementary solution, a sentence in the target language. So you have 1 million sentences, one supporting the translated sentence. And hence you know what the right answer is. That is a human curated, human validated data set is there which actually shows that you know what the right answer is. And you're telling the model what the right answer is. So yes, you need to have the right answers first yourself. Yeah, did I answer your question correctly? Yeah, that was your question?
I said going in is you don't know, it's random. So the right answer you might not know, right? So that's the part that I'm confused.
Yeah, so let me explain again.
Yeah.
So when you're training, you have for a language translation, you have a parallel corpora from English to French. You're training a model which will translate English to French. But you need to have 10 sentences in English, and for each of the sentence in English, you need to have a translated French sentence. So instead of 10, you actually need to have 1 million. So when you give an input as an English sentence, and then it thinks, oh, let's say, I am going to the movie. That's the English sentence. And if you're doing a French, I don't know how to speak French, but let's say it starts saying something like, the moon is bigger today. If that's the translation it thinks in French for this sentence, I'm going to the movies, you say, no, that's wrong. The right sentence is whatever is the translation of French. So that's where the right and wrong is. So there should be a data set provided by the human beings to have it. Okay, let's come back to sequence to sequence. So, yes, sir. Okay. That is the current research going on because it's so sequential, it takes so much time because it's computationally expensive. Every word you're giving an input, let's say, people have figured out how to convert a character and a word into a vector, into a single number, large, gigantic number, and you can input that. There is research for paragraph vectors, document vectors, people have done, so you actually can convert the entire document into one gigantic number and you can give that. I have not seen enough research on paragraph vectors, sentence vectors, and document vectors. I have seen lots of research on character level vectors and word level vectors. So even today, many of the papers when they publish for any NLP research, you have the inputs of text going in as a character or as a word. Sentence and paragraphs and documents, I have not seen enough papers. There are a few papers, but I have not seen. I will talk about when I say input A, input B, input C, what do you mean by input A? Is it just a character called A? I'm going to talk about it. It's not character A, it's a number. And how do I convert a character or a word into a number? That will be vectorization. I'll talk about that in a minute. But I want to conceptually explain how a sequence-to-sequence model works. Sequence model takes inputs in a sequence as a word or a character at this point of time. Yes, sir?
Yeah, I'm not very familiar with this thing, but will it be useful in understanding what to expect? What to make?
Yes, I'll have a slide on that. Hold on to the thought. I'll come back to it. You're talking about the mathematical equation or just the picture still? I'll come to that. I have not come to that yet. Yeah. But I'm just right now only focusing on this bit. I'll come to the mathematics in a minute. Yes. So conceptually, that's a model, a sequence to sequence. It takes an input. To represent the same thing in a mathematic way, the probability of y1 to yt, y1 to yt are the outputs of the model. The probability of these being the right answers given the inputs x1 to xt, because that's the whole concept you're trying to see, you're trying to predict the outputs based on the inputs. So the probability of outputs given the inputs being high can be mathematically shown as the probability of yt, that is the output at any timestamp t. So let's say output at this timestamp or at this timestamp, at this timestamp. So mathematically, if you generalize it, the probability of yt is dependent on a few factors. And what are they? The factors are, one is the previously outputted outputs till now. Let's say if the probability of an output of z is dependent on what were the outputs till now and what was the input context vector. So the input context vector is the v. So you have the hidden vector or a context vector. People normally use interchangeably. Some papers I've seen using context vector, hidden vector, but if you want to, a lot of people seems to be using nowadays hidden state, so you can use a hidden state. The output at any point of time is a function of what was the input hidden vector that came when the inputs were being given, plus all the outputs till now. That's what it is. So let me show the same thing from on this side for people who could not see. So the probability of outputs y1 to yt is dependent on the inputs, which can be shown mathematically is the product of the probability of each word at time step yt, which is dependent on the hidden state that came in after the input and all the outputs till time t minus 1. Yes, sir.
Why is it not V1
Okay. Yeah, okay. So in this model, the reason I smiled is actually I'm going to come to that slide, the point. In this sequence-to-sequence model, in one of the most fundamental sequence-to-sequence, people felt that after you give all the inputs what it needs and the hidden state which gets constantly updated, the last hidden state would capture the essence of the entire input. So I take one hidden state, which is the final hidden state of the input sequence. So the hidden state after I inputted end of sentence token here, that hidden state I take, that hidden state is coming in here, and I start outputting the first word. And it was accurate enough, but people came out with modifications to that, and I'll talk about those modifications. So the comment I think he mentioned, he said, why the hidden state v is a constant, why not you pick hidden state at every time step? And that's a suggestion people made too. So this is almost the same example and in a slightly different way. This is an upgrade from sequence to sequence. People said, hang on, in the sequence to sequence model, it's the same model which actually is reading the inputs and giving the outputs. In other words, it's actually sharing weights. They said, this is not going to work because the model is not that accurate if I share the weights of the input sequence and the output sequence. So they said we are going to have two different RNNs. One will take all the inputs and at the end produce a hidden state. I'll have another RNN which will take the hidden state of the previous RNN and starts outputting. So they called it as encoder and decoder, which is exactly the sequence-to-sequence model, but instead of sharing the weights, they use, instead of having the same RNN, same Lsdm being used, they use two different Lsdms. So you have one Lsdm which will only take the inputs and process it and gets the, becomes mature and intelligent and gives the final hidden state, which is this blue, the first blue arrow, and it then goes the new RNN, which is actually is called a decoder. So encoder-decoder as a concept, which is more of a breaking of a sequence-to-sequence model, and the only difference is you have two different RNNs, hence you're not sharing any weights, and consequently the model starts becoming more intelligent, but the rest of the functionality remain the same. You have a sequence of inputs coming in, and at every sequence you have the hidden state getting updated, and the last hidden state, which essentially captures the essence of the input, is given to the new RNN, and the new RNN starts using that to output. And at every time step again, the hidden state gets modified. It's, see, what is an RNN? RNN is nothing but as a big matrix of numbers which is randomly initialized to start with. Many times it could be zeros or it could be ones or just randomly initialized. And every time you give an input to the model and the model makes a prediction and the prediction is wrong, then you tell, no, that's wrong, the right answer is this. It does a loss calculation, and you think, with my initial matrix numbers, I got a wrong answer, but the wrong was so wrong, oh my God, I need to go back and change my matrix numbers. So it's called backpropagation, where you compute the loss and then go back and update your numbers. So I'm actually trying to make it as non-NLP as possible so that it's easy to understand. So you're actually having that weights which are getting modified. For the same, if you're using the same Lsdm to take the inputs and eventually start even outputting, people felt it was not as accurate. So they felt it was more accurate to use two different RNNs where don't